Okay, hi everyone. In this video, we are going to be looking at elastic potential energy, elastic energy per unit volume, and stress and strain. Okay, so we see that elastic potential energy is the energy stored when the material is stretched or compressed. So when an elastic material is stretched or compressed, energy is stored. Okay. And elastic potential energy has the formula half kx squared, which is also half Fe. Okay, if you remember from Hooke's law, we say that F is equal to Ke. Okay, so that means half Fe is the same as half into your F is now Ke, then times E. And that would give us half Ke squared. Okay, so that's how we come about that. So we can apply either half Fe or half Ke squared. Sorry, the x here, you can replace this with x, or replace x with E. They mean the same thing in this case, extension. Sorry for that error. Okay, so let's move on. So here we see some questions. This says a spring with a spring constant of 500 Newton per meter is compressed by 0.4 meters. Calculate the potential energy stored in the spring. So here we can say that the energy stored is half Ke squared. Since we are given K, our K is 500 Newton meters, and our extension or increase in length is or decrease in length, change in length is 0.1 meters. So we can say this is half times your K is 500, then your change of length is 0.1 squared, okay, which would give us 2.5 joules. Okay, so that's one. Now let's see another question. It says a spring with a spring constant K equal to 500 Newton per meter is compressed by 0.1 meters. Okay, what will be the speed of a 2 kilogram mass attached to the spring when released? Okay, this question has to do with conservation of energy. Okay, according to conservation of energy, energy cannot be created nor destroyed, okay, but it can be transformed from one form to another. Okay, so in this case, we can say that the elastic energy, which is half Ke squared, is the same as is equal to, has been converted to kinetic energy, which is half mv squared. Okay, conservation of energy is quite important. So we can say that half cancels half, and the velocity, if we make the velocity as the subject of formula, is going to give us square root of, that will give us Ke squared divided by m, making velocity subject of formula. So if we substitute the value, we are going to have K is 500 multiplied by 0.1 squared, then divided by the mass is 2. Okay, so that is going to give us root 2.5. The answer here is going to be 1.58 meter per second. Okay, so it's important to know that we can apply conservation of energy here too. Okay, so that leads us to another question here. It says a force of 80 newtons is used to stretch a spring by 0.05 meters. Okay, once released, what will be the kinetic energy of a 0.2 kilogram object attached to the spring? Okay, here, first of all, the elastic potential energy, let me call that EP. We can use the formula half Fe since we are given the force and used to stretch, and we also given the extension. So we can say that this is equal to half times F is 80, then times 0.05, okay? And that is going to give us 20 joules. Now, since energy is conserved, that means that the kinetic energy must be equal to the elastic potential energy, okay? And that is the answer, regardless of the mass, because it is the potential energy that will be converted to the kinetic energy. Okay, so that leads us to something else here, which is energy per unit volume. Energy per unit volume refers to the amount of energy stored in an elastic material per unit volume when the material is deformed or subjected to stress. Okay, so what that means is that energy per unit volume, let me call that EV, is supposed to be the energy, which is half Fe, okay, divided by volume. The volume of the material can be represented as area times length. Okay, so if you look at that, you can see that I can represent this as half times the force over area. Here is stress. Stress is force over area. We're going to look at that very soon. Then here is extension over length is strain. So this is the reason why we can represent energy per unit volume also of half stress times strain. Now, in the next videos, or in the in the next slide, we'll be looking at the relationship between stress and strain. Okay, so let's continue. So stress versus strain. Stress and strain are fundamental concepts in physics and material science that describes the response of materials to external forces. That means how materials respond when an external force is applied to them. Okay, so now we start with stress. Now the first thing is that stress is a measure of internal resistance a material the measure of internal resistance a material offers to an applied force. It is defined as the force acting per unit area and is represented mathematically as stress is equal to force over area. Okay, we've seen that earlier. So stress is actually the force that is applied on a particular area. Now, the third point, stress can be categorized into different types based on the type of force applied and the resulting deformation. So what that means, we have three types of stress. The first one is tensile stress, which occurs when the forces act to stretch or elongate the material. So if I have a material this way and I apply a stress that causes the material to elongate, something like this force here, F, causes this material to elongate. This kind of stress is called tensile stress. Now, the next one is what we call compressive stress. It's called compressive stress. Now, compressive stress arises when force act to compress or shorten the material. A very good example is spring. When you have a spring this way, okay, and you place an object on it, you see that the spring will reduce in size because of the load that you have placed on it. Okay, and this type of stress is called compressive stress. And we can see that there is a second, there's a third type of stress here. It's called shear stress. It develops when forces act parallel to the surface of the material. It develops when forces act causing it to deform or sliding or shearing. Okay. Now, a very good example is, let's say we have a material this way, and I apply a stress, a force on the, I think we can say, a horizontal force across the material, and it causes the material to more like slide this way. So you can see the sliding. Um, it slides this way. This type of stress is called a shear stress, and we are going to see more. Okay, so the last point there, let's note that stress is typically measured in Pascal. So stress has the same unit as pressure. It is measured in Pascal. Okay, so let's see the next, strain. Now, the first point, strain, represents the deformation undergone by a material in response to stress. It quantifies the change in shape or size of a material relative to its original dimension, and is calculated that strain is change in dimension all over original dimension. Okay. And strain can be categorized based on the type of deformation. So, the same way we have three types of stress, we also have three types of strain. We have tensile strain, which corresponds to elongation or stretching of a material, compressive strain, which represents the reduction in length or compression of a material. I've explained that. Then shear strain describes the change in shape resulting from shear forces. Okay, I've shown you what shear forces are. Now, finally, the strain is a dimensionless quantity. You know, when you say change in dimension over the original dimension, the unit is dimensionless. Okay, and often expressed as a ratio percentage, indicating how much a material has deformed compared to its original state. So, the summary for strain is that strain simply tells us how much a material has deformed compared to how it was before, the original position. Now, in terms of tensile strain, we can actually say that strain is equal to change in length all over length. Another way you can say that is extension all over length. Okay, we'll see more things there. Now, understanding stress and strain and their relationship as expressed in the stress strain curve is crucial in assessing a material's mechanical property. Okay, determining its behavior under load. Okay, designing structures, selecting appropriate materials for specific applications, and predicting the failure point or limit of material under different conditions. Okay, and in order to do that, we are going to be looking at a graph of stress and strain. Now, when we plot a graph of stress and strain, this is exactly what it looks like. And I want you to note the different points on the graph. We have point A, we have point B. Okay, this is point A, this is point B, point C, point D, point E. And each of these points represents different things, just like we have written here. You can see that from O to A, that is elastic behavior. I'm going to explain that, and the behavior here is elastic, okay, and why the behavior here is plastic. We're going to get the definition soon. But you can see that the point A actually is called elastic limit, even though is not written. The point A is called elastic limit. Point B is called upper. Is called the yield point. Point B, upper yield point. Point C is called the lower yield point. Point D is called the ultimate stress point. Okay, beyond that point, there's a fracture. Then your E there is the fracture point. That fracture is also called the breaking point. Now, but let's look at a very few notes on this. So we start with the elastic region. The elastic region refers to the portion of a stress strain curve where material exhibits purely elastic behavior. Okay, and you saw that in the graph. You can we can look at that quickly here. That is the elastic behavior. As long as the graph between OA this way, the material still has its full elasticity. Okay, now the next is the proportionality limit, also known as the limit of proportionality. Okay, refers to the maximum stress within the elastic range where stress is directly proportional to strain. What that means is that the proportionality limit is the limit where Hooke's law is obeyed. So that means for a material, an elastic material, Hooke's law is only obeyed in a particular limit. Beyond a particular limit, Hooke's law will no longer be obeyed. Okay, it says below this limit, Hooke's law applies. You see that? And the material deforms elastically, meaning it can return to its original shape after applied stress is removed without any permanent deformation. Okay, so now the yield point is the stress value at which a material begins to deform plastically. Okay, so this yield point now you have exceeded the elastic region. Okay, without any increase in the applied stress, it marks the transition from the elastic to what, to the plastic region, okay, of the stress strain curve during mechanical testing. Beyond the yield point, the material starts to undergo permanent or plastic deformation. Okay, when you say a material is plastic, we are going to see what that means very soon. It means it has lost its elasticity. So the point before the material loses its elasticity is called the yield point, where it has yielded its elasticity. Okay, so that leads us to the plastic region. The plastic region of a stress strain curve represents the range of stress beyond the yield point, where the material undergoes irreversible deformation. That means at this point, the material cannot go back to its original position. Not just that it cannot go back, it cannot even show any sign of going back. The material is plastic, okay? Now, in this region, the material expresses significant deformation without a, um, a proportional rise in stress, okay? Deformation in this region is not recoverable, and the material retains the changed shape even after the stress is removed. So when you remove the stress, the material still retains its shape. It doesn't go back to its original shape. So that's plastic. That's how to say a material is plastic. Now, then for the breaking point is also known as the fracture point. Okay, now if you keep applying stress beyond the plastic region, it means that the material would break, it will fracture. Okay, I read that again. The second point, the breaking point, also known as fracture point, is the stress level at which a material ruptures or breaks. Okay, it is the stress value at which the material fails completely, losing its structural integrity due to excessive deformation or stress, and cannot withstand any further applied load. That's important for us to note. Now, the third one, the term ultimate stress point generally refers to the maximum stress a material can withstand before failure or rupture. So, of course, every material has the maximum stress it can withstand before it breaks. Okay, during a mechanical testing, it represents high point on a stress strain curve indicating the peak stress value reached by the material before it breaks or fractures. This stress value is also known as the ultimate tensile stress, okay, in the case of tensile testing. Okay, that's important for us to know. So in the next video, I'll be talking about young modulus, bulk modulus, and shear modulus. Okay, please do well to subscribe to this video. Thank you for watching.